All right, so you guys got this packet here? All right, so we're going to kind of recap a little bit about kind of what we did in the lab today in terms of the overall findings in here. And then we're going to look at a few multiple choice questions that are kind of brain teasers more than anything. All right, so we've got these different spheres being launched. So let's start off first though with this. Something being launched horizontally from a tabletop, cliff, etc. Oh, I just realized I need to take pens as well, so I'll start that up. We got our lamp fixed as well, which is nice. Alright, so it says when something is launched into the air, its horizontal velocity does not change, its vertical velocity does. There are two general projectile motion setups we need to be concerned with. So that's what we saw in the lab, right? The x direction, the horizontal direction, we saw a nice linear position versus time graph, a nice constant velocity versus time graph. Velocity is constant in the x direction. However, in the y direction, right, the velocity is changing. So when we shot it at an angle, the velocity decreased on the way up, and it increased on the way down. So it lost speed on the way up because gravity is pulling it down, and then it regained that speed on the way back down from gravity. Now, most of the time, we're going to have it like that, where it's launched horizontally, all right? Where it's launched off of a cliff or a tabletop or a desk or something, okay? Where it just goes flying straight off. And in that case, the y velocity will just increase as it goes down. Kind of like the second video we analyzed. I just posted a video earlier about the lab analysis for the horizontal video. So when you go to do the back of the worksheet, the lab sheet, you should have, you should go reference that video. So it says sketch the trajectory of the object when launched horizontally from the surface on the chart above. So when you launch something horizontally, right? Here it is. When we launch it horizontally, that means the initial velocity is a y velocity. What we're going to do here is we're going to break our variables into the x and y direction. So when something's launched horizontally, its initial y velocity is just whatever speed you launch it at. Its initial x velocity is 0. All right? When you launch it at an angle, it has an initial, what am I talking about? I just said that all backwards. The initial velocity is the x velocity. The initial y velocity is 0. So when you launch something horizontally, you're shooting it in the x direction. In the y direction, it's basically just like an object that's being dropped. It's flying off and then it starts falling down. So it's flying straight while falling down. Kind of a cool thing. The trajectory, what does the word trajectory mean? What is that? Angle it's launched, that's part of the trajectory. That's part of the trajectory. The way it travels. It's the path of something that is shot through the air. So the trajectory is the path it's heading in. And typically a trajectory is like a set path. It's like, what's the trajectory of that plane? Or well, the trajectory is like, okay, if it kept going the way it is going, where is it going to end up? It's the path it's going to take. So the trajectory is the path it's going to take once it's launched. So that ends up being like a line kind of like that. And it looks just like it did in the lab, right, where we plotted the points. Those points we plotted on the video, that tracked its trajectory. All right, so does that make sense? All right. So now this sheet just kind of goes through some notes. It says some notes about this motion. Moves in the x direction with the speed it was launched. So the horizontal one, Tyler shot at about 5.5 meters per second. And we saw it stayed 5.5 meters per second the whole time it was moving forward in the x direction. All right. The initial velocity in the y direction is 0. If you go back and look at that graph we made for the Vy versus t, right? It went like this. Started off at 0 and then got greater, the y velocity, in the negative direction because it's going down. So that's the initial velocity in the y direction 0. The distance the object falls, so the distance the object falls while it's flying through the air, we're going to call that delta y. It's going to be the vertical displacement. Well, that delta y is simply however high the table, the cliff, the plane, whatever it is. Yes. It's however high the object is off the ground when it starts. So delta y is how far it's going to fall. Alright? So you can jot some of the stuff down on the paper, kind of write it down in here. It says how far the object moves to the right depends on how long it takes for the object to fall to the ground. So how far it travels to the right is delta x. Alright, so it's moving in 2 dimensions. The time it takes for the ball to hit the ground depends on the y direction. So typically, we're going to use the information about the y direction here to figure out how long it's going to take to hit the ground.
Any students remaining athletes who require COVID tests may proceed to the Denton Center for their test. Thank you.
All right. The ball accelerates in the y direction at 9.8 meters per second squared. So that we saw in the lab as well. So you think you're going to go for it? Get a shot. He's gone. All right. Jimmy went. So Tyler says, you know, I better go. Acceleration in the y direction is 9.8 meters per second squared. And usually, it's a terrible 9. Usually we make it negative 9.8 because it's accelerating down, right? Remember, it's the force of gravity, this can be off the screen, it's the force of gravity that's providing this acceleration, all right? So that's going to pull it down at a rate of negative 9.8 meters per second squared. So this is all just kind of summary of the lab on the front of this worksheet. Kind of the stuff you should have picked up. Now this next one, it's just a little drawing. But it's kind of an important drawing to make. Alright? So it says let's sketch a motion map for the object. First sketch a trajectory. Keep in mind it has to move the same distance with respect to the x-axis each interval. At the same time, it has to move more distance in the y direction each interval because the object's accelerating. Now, motion map, we didn't really talk too much about those at the beginning of the year. So I'm going to kind of ignore that wording. Alright. So let's say the ball started here, right? In the next time interval, let's say it moves to here in the x direction, right? It will have fallen down a little bit while moving forward, right? Let's say it fell down to about there, all right? So that's how far it fell down. Now, it's going to keep moving forward the same amount each time interval. So each second, it's going to still be here, right? However, in the y direction, it's got to travel farther than it did the previous time interval because it's speeding up, right? So it's got to travel a little farther each time. So it's not just here. I got to make it a little farther. I got to make this distance a little bit farther. Then the next one, right? Same x direction, right? But it's got to fall even farther. So I have to keep increasing the distance it falls in the y direction because it's moving faster as it goes, right? And that's why it ends up in this arced path. It ends up in this arced path because it's accelerating down. You know, next second travels even farther down, so maybe I make it like there. The next second, even farther down, maybe I make it there. And pretty soon we start kind of running out of board space because as you try to make this move faster and faster, downwards, that's what it looks like. Now, if I just drop something straight down, its motion map would look the same in the vertical direction as this one, right? It'd fall, something falling down would leave a path that looks like that. Well, it does that while it's moving to the side, while it's moving sideways. It's multi-dimensional motion, right? So the motion map ends up just being, if you put the velocity vectors on it, it's getting faster overall, right? Overall, it's getting faster because its velocity is increasing in the y direction. Velocity in the x direction is remaining constant. So it's getting faster overall. It's going to look something like that. All right. Let me see here. I want to do that demonstration right now. Yeah, I think I will. All right. Let me pause this for a second, and I'll. All right. So this is a cool little device. This really shows the fact that a projectile motion is a combination of two different motions, horizontal and vertical. So what it is, I have a steel bearing here. All right. And then there's this spring launch plunger in here. Okay. All right. So the spring launch plunger. You push the ball down. You set this little pin, right? You don't want to stick your head over it. Pull the pin, and it shoots the ball. Not very impressive, but, not bad. Let me practice. There's two holes. I always forget which one. So you pull the pin, and it shoots it up into the air. All right? So here's the deal. What I'm going to do is I'm going to give it a push, and pull the pin. Pull the pin. Give it a push. And while it's sliding, I'm going to pull the pin. Pretty constant speed, not bad. Alright, so the question is the ball going to, where's the ball going to land in reference to the cart itself as it slides? Where's the ball going to land?
Either behind it or in front of it. Mostly behind it.
You think behind it?
Yeah.
Alright. Okay, where's the launch room? It's going to go up, straight up, come back straight back down. Anybody else?
Well, it's gonna land in the same spot, but in relation to the thing that's
Okay.
behind it.
It's going to land in the same spot in relation. What was the last part of that?
But it's gonna be behind the car.
It's going to be behind the car a
Well,
little
it's
bit.
gonna be in the same spot as the launch.
Okay, so you say might land back in the hole because of the same speed. Alright, well let's see. We got some good answers. We got behind, mostly behind, maybe in front, and back in the hole. So we got a lot of options there. That's good. Alright, so let's see what happens. Back in the hole. You're right. You thought about it for a minute. Now Tyler, why did it land back in the hole? What made you change your... Right, so when you launch it in the air, right, it's moving at the same velocity as the car horizontally. When you knock it up, it's still going to have that forward momentum, that forward velocity. So it's a combination of being shot up in the air and coming back down, and it does that while it's moving to the side. And if you step back from a distance, it does look like an arc. If I push it a little faster, it's even better. Oh, that one missed. A little off track. The cart slowed down a little bit on me there. Let's try that one again. Oh boy. Good job. Spring's lost energy. It used to be, it's lost some of its strength. It used to be a little more. Alright, not bad.
Does anything affect it, like the weight of the ball or how fast the car is moving? Or
So,
would it be the same?
what would cause the ball to land behind it? What would cause it? Yeah, there's something pushing against the ball, like air drag or something. So that's why we got a nice heavy steel ball. I have a little plastic one there. Alright, I can do the same thing with this. This one, air affects much more. I think it gets launched higher too, so I think that's another issue with this one. I think it gets kind of crazy when you pull it in. Oh yeah, see, it flew that way in the air. So this one almost never lands back in it because of the effect of air, and you know, it's impacted much more by any irregularities as it leaves the car. Yeah, so see that one landed a little behind?
How about
See
the
that?
speed of the car? Like, did you push it fast enough for the ball to land behind it?
Well, you gotta realize, that's a good question. So the question is, can you push the cart fast enough so that the ball lands behind it? If I push the cart fast enough, I'm also pushing the ball faster, right? So theoretically, it should still land back in there. However, in reality, when I push it faster, it also slows, the cart also slows down faster. So sometimes what happens when you push it faster is the ball lands in front. Because it's more, it's louder. You'll hear it. When I push it faster, it's louder. So, see that? The ball hit right here and it came back up. So that means the cart slowed down more than the ball did as it was moving forward. So that's kind of the trick of that. So, perfect world, no matter how fast I push this, the ball is going to move right over top of the cart and land back in. Let me see that basketball. It's going to be hard to see this, but another classic demonstration is if you can run and drop a ball, just let it go from your hand as you're running. You know, the ball will fall next to you as you run, right? Right? It falls next to you as you run. When I released it, it had the same speed as me, right? Same speed as me, it falls down next to me. All right? Run. So fun. Am I running? Should I run some more? No? Oh, I got, come on, man. Come on. What do we do? It's for science now. Relax. For science. That's right. Come on. So, this brings up one of the classic problems in physics. One of the all-time great physics brain teasers. Now, I'll show you that video. Maybe I'll have you watch it tomorrow. All right. So in theory, right, if I drop this ball, right, at the same exact time, somebody throws the ball horizontally, like it's the same from the same height, right? If I drop the ball and throw the ball at the same exact time, they should possibly, maybe, hit the ground at the same time. Alright, so does it matter about the weight? Does it matter about the weight? Well, that's a very good question. If you ignore air resistance, the mass does not matter at all.
So, if you shot off a rifle round and drop that at the same time, it might fell to the ground at the same time.
That is true. Theoretically. So the question becomes, this is a classic Mythbusters video. Bullet drop versus bullet fight. Alright? So, if I was to, I used to have this great little tool that I could flick the corner of it and it would shoot a ball out and drop a ball at the same time. But from overuse it got broken. And I've never found one that has been as good. I've thought about trying to engineer one and 3D print parts of it, but I've done something with this piece of wood where, you knock it with a hammer and it drops a ball and shoots a ball. It's kind of a pain. But the idea is just like this. If this is the ball being shot, and this is the ball being dropped, they're going to fall down at the same rate. So even though this one's moving forward, it should hit the ground at the same time as the one that was just dropped. So Tyler's question is one of the first ones that pops up. So people say, "What's the way? You're telling me I had a bullet, right? And I had the gun, and I dropped the bullet, and I shot the gun at the same time. You're telling me the one that was shot will hit the ground the same amount of time as the one that was dropped? That's not possible." So Mythbusters did it. It's a really pretty good episode. I'll post a link to it in the course page. The whole episode is kind of long, but I usually show just the final little clip of it. What they did in the video, and I'll show you that clip now. What they did was they took a handgun to a gun range, right? And they figured out, they got it perfectly level, relative to the ground there, and they figured out if they shot the gun, how far down range the bullets would hit the ground, how far down they would land. And you gotta realize bullets do fall. Like, you ever played a video game that involves shooting, then you know. If you hunt and you sight in a gun, you know that. So bullets, they fall just like anything else falls. So you have to compensate for that in your aiming, right? You gotta aim a little higher than what you would what you're trying to hit. I mean, the extreme case is a football, right? If you're trying to hit, the corner of that fence, you would aim it up, right? You gotta aim high. You can't throw the ball straight at it. It's gonna fall down before it ever gets there. So, same thing with the bullet. It's just moving fast forward. That has nothing to do with, just like you saw in the lab, moving forward has nothing to do with how it falls. Alright? So, they figured out where the bullets hit the ground because air drag does play a big effect on some things that are moving fast. But it only plays an effect in the direction of motion. So the air drag does not affect the fall rate at all. It's very, very cool the way that works. So they figured out where the bullets were landing in the gun. They rented out a huge airplane hangar, right? And they made a device. It was really pretty cool. It rigged up the gun in a electronic trigger system. So when the bullet left the barrel of the gun, it triggered an electromagnet that was holding a bullet, the same size bullet, way down range where the bullet would land. And when that gun triggered the signal, it would release the bullet down here to ground. So while this one's falling through the air, the bullet is coming from way down range, and they set up a camera to see if they hit the ground near the same spot at the same time, see if the physics works. Alright? So it's pretty easy to find this video. It's on YouTube. There's been a few versions over the years. I seem to remember last year when I went to find it, I couldn't find the exact one that I usually use. Alright? I'm going to turn off the light, so probably isn't going to help too much how bright it is